So hi everyone, I'm Logan Lee. I'm a master's student in atmospheric sciences from the University of North Dakota. And after this, I'll be going back there to try to finish up my master's degree in the next year. And so this summer I was working with Ayumi and Eric on Great Lakes ship data. So that's what I'm going to present to you today. So a little outline of what I'm going to show you today. I'm going to give you some background information on meteorological and ship data in the Great Lakes. And then I'm going to go over some methods on how you actually look at ship data. Then I'm going to show you some results of comparing that with buoys and also with different forcing models. And then I'm going to leave you with some applications for winter and summer and a summary and some future work. So first, the background. So meteorological data in the Great Lakes mostly consists currently of observations from seaman or Coast Guard stations, buoys, surface stations, ships, and satellites. We also use reanalysis and models such as HRRR and CFSR for other data sources, and also interpolated meteorology, which ingests the seaman, buoys, surface stations, and satellite water temperatures, but currently not ships. And you might be asking, well, why? Well, there are some difficulties with using ship data. They're mobile, difficult to standardize, and ships require adjustments, especially because they're varying heights above the water. And also, ships they're infrequent and they're not consistent spatially. So on a given day, you might have a lot of ships in an area, and the next day you might have none. So those are some of the challenges with using ship data. That said, there's actually a lot of data out there. In 2014 alone, there were over 30,000 meteorological reports from 28 ships in the Great Lakes. And what makes this really good data is that a lot of it's from open water locations. And so over open water, our sources of observations are more limited to mainly buoys and also satellite. And so especially when the buoys aren't out, ships have the potential to fill kind of that need there. And so there's a lot of data out there, and there are some challenges with using it. So we want to know, well, can we use it, and should we be using it? And so here's just kind of to illustrate how much data there is. If you look on the chart on the left, you'll see it's a histogram showing the number of data reports from the ships over the year per day. And you can see that around the summertime to early winter, there could be over 100 reports per day from ships. It drops off in the winter with ice cover and poor weather conditions, but there are still observations there when the buoys aren't out. And then also, if you look on the right, you'll see kind of a map of where these reports are coming from, and you see the shipping lanes are really well defined. And so there's a lot of data out there. We just need to know whether we can use it. And so now I'm going to go over some methods on how we analyze ship data. So what we did was we considered air temperature, wind speed, and dew point. But for this presentation, I'm only going to focus on air temperature, both for the sake of time and because it was our most well-developed analysis. So we did a lot of quality control to make sure that our data points were usable. And then we decided to compare that with buoys and also with HRRR, CFSR, and interpolated meteorology. So I'm going to go over some results from that. So I'll start with the ship versus buoy. We wanted to know, do nearby ships compare well with buoys? And one of the reasons is because HRRR, interpolated meteorology, and CFSR all ingest buoy data. And so we figured if the ships don't agree well with buoys, it probably won't agree well with any of these other sources. And also buoys are a good source of open water observations, so it's nice to compare with for ships, which are also open water. So if you look in the chart on the left, you'll see a time series plot of the ship and buoy temperatures, where the ships are the dots and the buoy is the line. And what I just want you to notice about this is that there's fairly close agreement between the two. And again, on the right, you'll also see a one-to-one relationship plot between ship temperature and buoy temperature. And you can see that the ship and buoy temperatures fall along that line, which indicates a perfect relationship. They're not on the line, so it's not a perfect relationship, but the root mean square error was less than a degree. And so from this, we were pretty confident that there was good agreement between ships and buoys for air temperature at least. So once we were more confident that we could use the ship data for air temperature, we decided to compare it with kind of three different forcing models that we use. We have the high resolution rapid refresh, or HRRR, which is kind of a nowcast model. Interpolated meteorology, which I've labeled as a hindcast nowcast because it can be used as either one. And then we have the climate forecast system reanalysis, which is a hindcast. It's done in retrospect after the fact. So I'm going to start off with talking about the HRRR. So the HRRR is kind of NOAA's newest high-resolution atmospheric model that uses data assimilation. And so when we compare the HRRR with ship temperatures, and this is a time series, and you might notice that it doesn't run through the whole year, and that's because we only had partial HRRR data for 2014. But if you look at the HRRR temperature points in green and the ship in purple, you'll notice that especially in the wintertime, the HRRR tends to be lower than the ship temperatures. And you can really see this in the HRRR minus ship temperature difference plot in the center. You can see at the beginning of the year, you have HRRR temperatures that are much lower than the ship temperatures. And also, this kind of reinforces it, the one-to-one plot showing HRRR temperature versus ship temperature. You can see that especially in the beginning of the year, the HRRR temperatures fall below the one-to-one line, indicating that there is the HRRR temperatures are lower there than the ship temperatures. And also note that the root mean square error here is 2.9, so that's higher than we found between ship and buoys. So what we got out of this was there was less agreement for air temperature than with the buoys. And also that there is a notable cold bias in the winter. So next I'm going to talk to you about interpolated meteorology. And this is kind of GLERL's in-house run meteorology, and we can run it back in time for when we want to, or we can use it for a snapshot of now. And so the same kind of plots as before, I'm going to show you the time series of ship and interpolated temperatures. And here you'll notice the interpolated temperatures in green, especially in the early part of the year, the winter time, are higher than the ship temperatures. So kind of the opposite of what we saw with HRRR. And if we look at the difference plot, you'll actually see this again. At the beginning of the year, the interpolated are much higher than the ship temperatures. And then if we look at the one-to-one plot, you can really see this well. There's this little tail on the left-hand side of the plot, and this is kind of where the interpolated temperature levels off compared to the ship temperature. And so also our root mean square error is 3 here. So from this, we determined that there's less agreement than with the buoys and with the HRRR for air temperature. And also this time there's a warm bias in the winter compared to ship air temperature. But I should also note that since 2014, when this data was from, there's been an improvement to the interpolation method. And so this might not represent what the current interpolation would do, but this is what our historical archive data shows. And so we thought that was still a valid comparison. So next I'm going to talk to you about CFSR. And this is a reanalysis that can go back to the 1970s. And so it's really helpful for us to look back in time. And if we look at the same kind of plots again, you can see the temperature time series. There really aren't any noticeable large differences between ship and CFSR. And again, with the difference plot, you can see this. There aren't really any large biases either way for any particular time of the year. And also the one-to-one plot shows most of the points falling along the one-to-one relationship line. And also your root mean square error at 2.13 is lower than for HRRR and interpolated. So from this we got that there's better overall agreement with the ships for air temperature than with the HRRR and interpolated meteorology. However, if you notice in the difference plot during the summertime, there are a few larger outliers than when you compared it with HRRR and interpolated meteorology. So we thought that was kind of interesting. So now that we kind of looked at that, how the different real casts and nowcasts compare to the ship temperatures, we're going to look at some applications. And we're going to start with the wintertime application comparing kind of our HRRR and interpolated, our nowcast products. And so what we found with HRRR and interpolated is that there's actually interpolated air temperatures are warmer than the HRRR in northern and western Lake Michigan. And we thought this could have some potential implications for ice forecasting. And so we wanted to know, well, how do we know which is correct? And we thought, well, maybe ships will help us answer this. So here we have a map of the January 2014 interpolated minus HRRR average air temperature over Lake Michigan. And you can notice that there's a lot of red and orange in the western and northern parts of Lake Michigan, and that's where you have your largest temperature difference between interpolated and HRRR. And also I've overlain all of the January ship reports, and fortunately for us, they fall right along that large difference. And so I have them highlighted here. Yeah. So to compare this, what I did was, in the first plot, I took all of those ship points and I matched them with their corresponding HRRR and interpolated temperature point. And then I plotted them on a time series like you've seen before. And you'll notice that the interpolated in purple tends to be higher than the HRRR, which is in maroon. And then the ship points tend to be kind of in between, but closer to the HRRR. And so that compares well with what we saw overall in the Great Lakes, where you had HRRR was a cold bias in the winter compared to ships, and interpolated was a warm bias. And also, if you look at the bottom plot here, you can see this is a one-to-one plot between HRRR and interpolated temperature and the ship temperature. And you'll notice that HRRR tends to fall below this line and interpolated tends to fall above it, especially in the wintertime. And so that just reinforces our biases that we found. And so similarly, we wanted to look at CFSR versus interpolated. These were, both of these can be used as hindcasts, so we wanted to know, we wanted to look at some differences between the two. And we actually saw there was a summertime nighttime bias present between the two, and we thought this could have possible implications for, say, heat budget in the Great Lakes if you were to calculate it later. And so if we look at this, you'll see a map on the right of the interpolated minus CFSR 2-meter air temperature at 10 UTC July 2014, and this is an average. And we picked 10 UTC because this is around the time you'd have your morning lows in the summertime. And so we picked 3 points, one from near the Straits of Mackinac, one in northern Lake Michigan, and one in southern Lake Michigan. And the corresponding temperature time series are on the left for each point. And this is CFSR is in the maroon color and interps in the purple. What I want you to notice is that where I have highlighted in these red circles are actually large differences between the two, and predominantly at nighttime. And so we were wondering, well, what's going on here? Which is more correct here, at least as far as can ships help us? And so here's the same map, but with the ship points overlain. And if you plot the same time series, but you add the ship points as the blue dots represented on the graphs on the right, you'll see that for the Mackinac Strait point, the blue dots actually tend to line up better with the interpolated meteorology. However, if you go to the northern Lake Michigan point, you actually find the opposite. And the blue dots, the ship points, tend to match closer to the CFSR temperatures. And in southern Lake Michigan, it's a little more inconclusive. We have a lot of points, but they don't really match up well with the largest temperature difference areas. But what we wanted to take home from this is that even within the same lake, there are in different regions in the lake, there are differences between the models and their biases. And so ships were really able to kind of help us determine where these differences are. And so in summary, ships represent a wealth of underused offshore meteorological data, and they can help us to reveal the biases in our current forcing models and reanalysis, both overall and in different locations within each lake. And also, in turn, these biases could have some large implications, such as on ice forecasting with poor winter forcing and the heat budget with poor summer and nighttime forcing. So some future work that could come out of this. We'd like to expand HRRR to include the full year so that we could more directly compare it with CFSR and interpolated meteorology. We'd also like to utilize the ship observations and also the results we found with biases to maybe try to improve our ice forecasting. And lastly, we'd like to try to maybe get a standardization of ship data, both reporting and usage within NOAA, because it was really difficult to it's really difficult to use because you need to have all the heights, and if things don't match well or they're not reporting in the same way, it can be difficult to use that data. So in the future, it'd be helpful to have a more standard way to use it. So I'd like to thank Ayumi and Eric for their mentorship and guidance, and also Greg Lang for all of his help with the interpolation, regridding, and answering all of my questions. And then also just CILER and GLERL in general for this opportunity and for making it a fun internship. So with that, are there any questions?
So in those scatter plots, how did you compare the sheet data with those analyzed data?
Yeah, so what I did was I matched the ship data, each ship data point, with its nearest analyzed data, nearest data point. And so like for her and CFSR, and what we actually did was we put the CFSR, the HRRR, and the interpolated meteorology. Well, first we did it that way, and then for the applications, we actually put them on the same grid so that we could directly compare. And so mostly it was just matching with the nearest point that had valid data. So, yeah.
Talk a little bit about the outliers and the different spots. I think it was like slide 7.
Yeah. CFSR, I think.
So I guess,
there we go.
Yeah, I was just wondering, so I definitely see the outliers too. It almost seems like there's a little bit of a trend that for some that there's just more of a difference. And kind of as the year progresses, it's less.
Yeah.
And I saw that when you were talking about the difference last too. Do you have any like insight as to why that might be?
So part of it might be that there's just more ship data in the summer. So yeah, maybe overall you have more points or you'll have a wider spread because you have more points to look at. So that's a possibility. And then with CFSR, also its resolution is somewhat more coarse, so it's possible you could get some points that are really different along the edges of the lake. Yeah, yeah. Yeah.
How are the ship data ingested? Like how is that being transmitted and at what kind of time, frequency, and spatial frequency?
So I don't know if you're familiar with the NOAA port webpage. It shows, so basically those files are, that system, there are files, they're LMD files that have all of the ship observations. And basically the frequency of the ship reporting, I think, just depends on the ship, you know, how often they want to report. And so that can be an issue. But for the most part, when we looked at that briefly, and it looked like it was relatively constant, a relatively constant amount over the time of day. And so there weren't any like huge lulls in your daytime reporting. I don't know if that kind of answers.
Was there metadata in terms of like the sensors and its specific platform locations where you could potentially correct it?
No, so GLERL has a ship height file, and that's really the only thing we have. And we tried to reach out to the port meteorological officer for the Great Lakes, and we got a file that contains some more anemometer and thermometer heights, but they were above a certain line on the ship and not necessarily the water level, so we weren't sure how to be able to use it yet. So we didn't incorporate that, but that's definitely where standardization might help with this.
Well, that's great. The summer bias, is there a potential when maybe the air and water aren't really driving a big difference, but you're just latent feed on the ship could be more, and that could be affecting ships? Yeah,
you know, I haven't thought about that. I guess it's possible the ships could be heating up more, but I'm not sure if they have a way to correct for that. Because I mean, if they're using standard meteorological equipment, that might be kind of like summertime here on land. You might expect that too, but we try to aspirate and things to prevent that. I'm not really sure what they do on the ships, though. Yeah, that's a good point. Yeah.
I wasn't sure what ships were included. Are any of the GLERL boats providing data?
I'm not sure. I don't think so, but and maybe they could in the future, but
most aren't running with meteorological sensors that are probably appropriate.
Yeah.
Anything else, Logan? All right, thank you very much.
Thank you.